Okay, so we are going to go over the worksheet that was for today, September 20th, just to kind of go over the math part. If you were stuck, this is maybe will help you. Before we start the part that's up here, let's review a little bit about metric. So it's important to remember how the metric system works. So some teachers like to teach a little saying that King Henry died by drinking chocolate milk. And this is just a little way to remember all the prefixes for the metric system. So K is kilo, H is hecto, D is deca, B is the base unit, so that would be like a meter, a gram, an amp, a liter, and any base unit else of measurement we would use. The other D is deci, and the other C is centi, or the C is centi, and the M is milli. And these are all based off of 10. So if we take the base and say it's 1, anything above it is divided by 10. So a deca is 0.1 of the base unit. A hecto is 0.01, and a kilo is 0.001. A deci is like a decimal, so there's going to be 10 of those. A centi is 100, and a milli is 1,000, just like the Spanish is. Deca, diez, 10. Centi, century is 100, and milli, like mil, is 1,000. So going this way, 1 meter, 1 base unit, whatever it is, gram, amp, liter. And the same would be, it would be 10 decimeters make a meter. 100 centas make a base, and 1,000 millas make a base. But then this way, it's and the thousandths, so 0.10, 0.01, and 0.001. And the way this helps you is you can hop along the thing. So if I have 50 grams, which is a base unit, and I want to know how many milligrams it is, I hop from the base unit 3 jumps over to the milligram unit. And the 50, we know that there's a decimal that's just right there. We're going to create 1, 2, 3 more spaces for that decimal. So 50,000 milligrams are in 50 grams. And if I wanted to go to kilograms, how many kilograms is 50 grams? Well, I'm going to hop 1, 2, 3 that way. So I would take this decimal and go 1, 2, 3 that way. So it would be 0.050 kilograms. So this just helps you to do it quickly. You can just memorize it and just know this is, you have to times it to go this way, and you have to divide it to go this way. This is just practice, and so it's just something you have to get better at as you do it. So let's look at our problems from earlier. The first video, which was this number 1, it had a rotor, and it had some wires to connect a little light bulb, and there was a string with a weight on it. And as the weight went down, it pulled this generator, and it made the light shine. So potential energy is the energy something has before it starts moving. So when the weight was up top, it had potential energy. And all we're doing in this square is calculating how much potential energy that weight had sitting at its highest point. So on the video we watched, we found out that the weight had a weight of 2.198 pounds. But we also can see that the weight needs to be in newtons, not pounds. So we have a conversion right here that tells us how to change pounds into newtons. So what happens is 4.45 newtons are in every pound or per pound. And in class we talked about if there's something on top and something on the bottom and they're the same, we can cancel them out. Just like if it was two numbers, you could cancel them out to be one. So we're going to cancel out these pounds because I have pounds on the top from my weight and the conversion factor. There's 4.45 newtons per pound. And then I can just multiply that on my calculator, and that gives me a number. I didn't have my calculator out. Hold on. So if I do 2.198 times 4.45, I get 9.78 newtons. Now that's just the weight. And this equation has the weight times the height. So I have my weight, but now I need to do my height. And in the video, the height was 82 centimeters. So if I look back at my centimeter conversion, I have centimeters and I want to go 1, 2 over to meter. Centimeters to meters. So I can see there's 100 centimeters in every meter, or I can hop my decimal over 1, 2. So if there's 82, I'm going to move this decimal over 1, 2. That's the same as having 0.82 meters. Or if that's confusing of what I did, you can say 82 centimeters, and there's 100 centimeters in a meter. Now my centimeters cancel, and that leaves me with meters, and 82 divided by 100 is 0.82. So now I have my height. Now the final equation is just my weight in newtons multiplied by my height in meters. So we changed all the numbers to get there. So now I take 9.78 newtons, multiply that by 0.82 meters, and that in my calculator will give me, rounded off, 8 joules of energy. Now this is all of the energy that could be from this weight going down. This next part is the amount of energy that actually went to the light. So in the video, again, we were told that the light bulb is a 1.6 volt light, and the current on the little meter in the video was 5 milliamps. 5 milliamps. And that was the current. So I'm going to put C for current. And then I timed it on the video, and it was 17.43 seconds. Okay, so I have my volts. I have milliamps, not amps, but I have seconds and time. So the only thing I have to fix here to put in the right units to use my equation is these milliamps. So again, going down here, milliamps are 1,000 millis in an amp, or 1,000 is 3 jumps over to the left, from milli to centi to deci to the base. So if I had 5 milliamps, I need to move my decimal 1, 2, 3 over. So it's 0.005. Oh, sorry, it was 50. Man, I blew it. So sorry. It was 50 milliamps. I just looked at my thing. I thought that number looked funny. So I went over too much. 50 milliamps. So I'm going to go 1, 2, 3 to 0.050. That sounds right. So that equals 0.05 amps. I just converted the milliamps to normal amps. So now I have a 1.6 volt light times my current in amps, which is 0.05 amps, times the time it took, which is 17.43 seconds. If you put that in your calculator, you should get rounded up 1.394, so I'm just going to say 1.4 joules. And then all this last box is saying how efficient was that? And efficiency is just your output divided by your input divided by 100. So this is your output, this is your input. So we just are going to divide these two numbers. 1.4 divided by 8 times 100 to get the percent. And that gives you about 17.5% efficiency. Okay, so then the second video, we looked at the water, and we had the jug of water way up high and a little spout that came down a tube and went into a little generator that spun around and connected to a light bulb, and the light bulb lit up when the water was pushing through the generator. So in that video, we had the jug of water weighed 38.2 pounds, and it was at a height of 179 centimeters. Okay, so for that one, it's just the height times the weight. But again, the weight needs to be changed from pounds to newtons. It's the same thing we did up here with a different number. So 38.2 pounds times 4.45 newtons per pound. My pounds will cancel. And then I'm going to do this all in one string just to see if you understand what I'm doing. So then I also need to times it by 179 centimeters, which I know there's 100 centimeters in 1 meter. So I can cross this out. So in this problem, instead of doing two equations, I just did it in one big long string of equations. So here I took and I found out my weight in newtons, and then I figured out my length in meters. Well, here I figured out my weight in newtons, and then I figured out my height in meters, but I just did it in one big problem to keep it all on one section. And I can just multiply all the stuff on the top, and I can divide all the stuff on the bottom. And if I do that in my calculator, I should get 304 joules. Then looking at the video again, it's the same thing as up here. Our voltage is still 1.6, and this time the amps were 25 milliamps. And the time at this one was 178.5 seconds. 178 seconds. So I just need to make sure everything's in the right unit, and then I can multiply it. So the volts are good. 1.6 volts times, oh, we have this milliamp again, just like we had it up here. So this time we have 25 milliamps. 1, 2, 3. So it's 0.025 because milli is here and amps are here. So we just move a decimal 1, 2, 3 times to the left. So times 0.025 amps times the time, which is 178 seconds. If you put that in your computer calculator, it is 7.1 joules. And again, to figure out the efficiency, it's just going to be 7.1 joules divided by 304 joules times 100. And that'll come out to about 2% efficiency rounded. So even though this second system had the potential to give us much more energy than the first system, it was much less efficient than the first system. All right, then the third one is air. And air does things a little differently, but that's okay. So in the video, we found out that the pressure was 30 pounds per square inch. That's what PSI is. And we also found out that the air tank was 6 gallons. Now, to find the potential energy with air, we need our PSI in pascals and our volume in meters cubed, not gallons. So we have to change both of these numbers to be the right units. So 30 PSI times 6895 pascals per PSI, because it says there's 6,895 pascals per PSI. So these cancel. I'm going to move that 6 gallons just so it's not confusing. And then I also know that I have a 6-gallon tank, and I also know that there's 264 gallons in a cubic meter. So now I have this big long problem. I'm going to do 30 times 6895 times 6 divided by 264 on my calculator. And if I do it right, I should get about 4,700 joules rounded off, which means this has even more energy potential than the other two. So let's see what it gave us in the light. So we've got our light bulb, 1.6 volts. And we know from the video that the current was 15 milliamps. But we also know how to convert milliamps into amps. We're going to move the decimal over 3 spaces, so 0.015. So that's going to be 0.015 amps. And then we're going to multiply it for the amount of time. And this one, the time was 54 seconds. That was off the video. So if we multiply those 3 numbers, we get 1.296 joules. So I'm going to round that to 1.3 joules. Okay, so we wanted 4,700 joules, and we got 1. I don't think that's going to be very efficient. Let's find out. 1.3 divided by 4,700 times 100 gives us 0.02% efficiency. That's terrible. So even though the bottom one had the most potential for energy, it did the worst as far as efficiency goes. So there's trade-offs that are going to happen, and some things have a lot of potential, but they lose a lot of energy in the systems, and there's a lot of room for us to improve our engineering to make it more efficient. And that's kind of what we're going to look at in the next lesson.